Okay, hello everybody. I've literally just arrived in my office a couple of minutes ago, straight from London at an event with the British Physics Olympiad. So I know that I probably saw some people there. This was a great thing for those who did really well in the various kind of challenges that they'd had over the year. And also there was a lecture later on that was pretty technical. So that was like the British Physics Olympiad event that I was with. So if anybody was there, yeah, it's great to see everybody. Now, today we're going to start with some GCSE. I've kind of updated the front page of my GCSE website to kind of really highlight the two big things that will help you this year. First of all, I've got my practice papers. If you do those, that's going to help improve your grade. And also there's a link to the live stream. So if you click on this, this has now the updated live streams up until the end of May. So obviously in addition to what we're doing today on the 25th, you can see the schedule for all of the live streams that we're doing for the rest of the month. But basically today, if you click on that thing, it takes you down to this one over here. We're going to be looking at atoms, which is going to help with your GCSE revision, and also energy stores as well. But it's great to have so many people in the chat already. Hi to Katsuri, Chop, Matthew, Just a Person, Joshua, Joe, Anissa, hello everybody. Hope all of you are doing really well, and also anybody who's just joined. If you can't get in the chat at the moment, make sure that you just subscribe to me on YouTube. I think, let me just check my phone. I just want to see the actual number of subscribers on the channel. So at the moment, I can see, oh, we have passed it. I'm at 175,021. So I think earlier today I got past 175,000, which is a nice big number. It's a nice kind of 1 3/4 100,000. So that's brilliant. Hello James. Hello Adrielle. Everybody else. Right. So 175,000. That's a lot of people. Okay, so if you want to say hello or anything in the chat, I will try and read it as I'm doing the stream. If you have any other questions about what we're doing, ask away, and I'll see what I can do as I sort of read the questions as we go on. So let's have a look at the first question. Timodola, hey, hope you're doing well. So more than 100 years ago, and the first part of this question is really just building the pictures, and actually just by reading the question, that already gives you information about some of the physics discoveries. So more than 100 years ago, Rutherford's investigation into alpha particle scattering led to the idea of the nuclear model of the atom. So the nuclear model has this nucleus in the middle where most of the mass is. Complete the following sentences. Oh, I actually just kind of pretty much answered it, didn't I? So the nucleus of an atom is where almost all of the mass of an atom is concentrated. So that one there is a fairly kind of straightforward one. The slow-mo, yeah, these are from the practice papers that are available to buy. So if you want to work through this yourself in your own time and do the other questions I don't cover in the stream, then you can just buy a set. They don't cost much money, I don't think, for the amount of work that's gone into them and how useful they'll be to you. Yeah, right. The nucleus of an atom is where all the something in the atom is concentrated. So basically, it's where almost all the mass is, because although most of the mass is in the nucleus, we still have the electrons that orbit it, and they have mass as well. But all of the something is concentrated in this one bit, and all of the positive charge is concentrated in the central nucleus. So almost all the mass, but all the positive charge. Okay, and that is the nuclear model of the atom. Now, of course, you need to know about how this model has changed over time. We now know, for example, that the model has developed since then. But before they had this nuclear model, they thought that this was like a suitable thing, and that kind of made sense. So this is the plum pudding model. The plum pudding is just an old name for some kind of dessert that had like raisins or I guess plums throughout it. I've never actually seen a plum pudding being eaten. I've never seen one for sale in any restaurant. I've never seen one for sale. So I guess you could make your own one. The plum pudding model was developed after the discovery of one type of subatomic particle, state-rich particle. As a few people have said, like Zeno, the answer is the electron. And basically what they thought was that the small red things here are the electrons, and so these are negative, I'm just going to put a negative sign like that. And that was basically in this sea of positive charge. Okay, so that was kind of like the model that we had before. I guess here we've got 6 electrons, so I'm going to put 6 pluses to show that we have this kind of randomly distributed kind of positive charge. It was only later when we actually had this nuclear model that we realised that there is this dense central positive nucleus surrounded by lots of empty space and then the orbiting electrons around that. Okay, a ball of charge with negative electrons. Temedola, yeah, exactly. So Chop and Slow-Mo and Zeno are correct. The Slow-Mo says you like plum puddings. Fair enough. Explain why after Rutherford scattering experiments that we talked about earlier on in the question, in which alpha particles were deflected and even reflected. So the alpha particle, I'm just going to draw on down here. So this is my alpha particle. It's got 2 positive things in it. It's got a couple of neutrons. They didn't know that at the time. They just knew that the alpha particles had a positive charge. Okay, they're quite small, but they have a positive charge. They were deflected, which means they were bent, and then reflected meant that they actually sort of came back. And basically, what we found was that the plum pudding, I suppose that should be lowercase rather than capitals, the plum pudding model could not explain the experimental results. Okay, so the idea of the model in science is to kind of try and model what's happening in the world around us. Now, this model couldn't give any satisfactory answers to why these positive things went straight through it and some of them actually kind of bounced back. So we can then say that the new model with a dense positive surrounded by empty space. So the new model with a dense positive nucleus surrounded by empty space could explain the results. And basically, it's because we have this dense positive core that then can deflect these positive alpha particles, or it can even reflect the alpha particles back again. Yeah, and also, as Joe Smith said, which I probably didn't write as clearly here, the experiment also suggests that atoms are mostly empty space, as basically most alpha particles pass through the gold foil unaffected in their travel path. Exactly. And yeah, this is identical to the stuff in GCSE chemistry. Okay, oh, here we go. Now this one over here, it's a 4-mark question. So the first thing is that when you see a big question like this, don't worry about it. Okay. Also realise that sometimes there might be the opportunity to draw a diagram to help explain your answer. So what I'm going to do over here, I'm going to do some circles like this. And I'm going to do a big circle around here, and then I'm going to do some smaller black dots. Okay, now this one over here is going to be my Rutherford model. Okay, so what we have is we have electrons out here, and we have a positive nucleus. So that was like the first model, and that kind of made sense. We've got this dense positive nucleus, lots of empty space. The other model I'm going to do over here, I'm going to do something fairly similar, but I'm going to colour sort of some of these in a bit like that. And then what I'm going to do is what all of you know from GCSE chemistry, is I'm going to do a couple of shells with some electrons in. Okay, not even to the same kind of level of detail that you go into in GCSE chemistry. So basically we still have electrons, but what we have now are shells, and we also have neutrons plus protons in that nucleus. Okay, so what we've done is we've developed this initial model as things were later discovered. Now, so people are saying stuff like Zeno saying that current model has neutrons, but Rutherford models didn't. So what we might just say is describe the differences between the nuclear model and our current model. So our current model has protons and neutrons in the central nucleus, and then you want to sort of compare it and actually make it very kind of clear. Would a diagram be accepted in the mark scheme? I think, Victor, that you've got a good question. I'm going to talk about that. So so basically, so that's our current model, but then you might just want to compare that and just explicitly state it. Rutherford's model only had protons. Okay, so we've talked about the fact there's now these neutrons in the middle. We can also say that electrons exist in distinct energy levels, or you could say, or shells. So that's something else. Okay, so I think, okay, there's some good questions here. I don't actually know the answers. So, did Rutherford's model suggest that electrons were in fixed positions before Niels Bohr had discovered that they orbit the nucleus? I don't think so. I think that they just talked about maybe electrons being a long way, and I think they probably would have said they orbited because they realised that the electrons are negative and this was positive, so they had to be moving around, otherwise they'd be attracted straight in. So I think, and this isn't something I'd actually definitely know, is I think they talked about orbiting electrons, or like a cloud of these orbiting electrons, but I don't think they said that they definitely didn't say they existed in different distinct energy shells. Okay, in our current model. Now, of course, somebody asked the question there about does this change at A level, and then I guess beyond A level at university level. Yeah, so for example, when you go onto A-level physics, you realise that the protons and neutrons are actually made of smaller things called quarks. Also, that the electrons can exist as a kind of wave that has, and that's why we have these distinct shells, because we basically have a standing wave of the electrons. As they're moving, they behave like a wave, and you can only have certain effectively fundamental frequencies that these waves can sort of fit into as they go round. And also then later on you realise that occasionally, due to this kind of probability shell of where the electrons are, because we don't exactly know their definite position, there's times where the electron actually, there's a probability of the electron existing within the nucleus for a short amount of time. And also the nucleus has different energy levels and it can get excited and so on. So like anything, you can start to kind of take this model and develop it further and further and further. But I think that's good enough for GCSE. Okay, Joe Smith says this gives you GCSE nostalgia. Yeah. Okay, so yeah, like Victor said, the model does change slightly when you go to A-level. Things do change very slightly, but I think what you need to just remember is it's only GCSE, okay, and therefore it's not going to be impossible. Okay, yeah, there's Slow-Mo talking about the Heisenberg uncertainty principle. Yeah, that comes into it. So, you know, if you know the, you might know the momentum, but you don't necessarily, if you know its speed, you don't necessarily know its position and all of this stuff. So yeah, let's not go there. Let's just keep it GCSE today. Right, so that's the first question. Again, that thing there, you need to know about the models of the atom for both physics and chemistry. Okay, is it 27 days until your first paper in physics? Actually, I'm just going to have a look and see what the date is. So the date for your first paper is, because I've got it here, your GCSE paper 1 is the 22nd of May, which I guess is about, yeah, 27, 28 days, which gives us 4 weeks. And basically, I'm going to be doing these live streams all the time. So if you know that you're in a good position now, just imagine what it's going to be like in a month's time. So yeah, you do have other papers like your biology and stuff, which I think is on the 9th or is it the 12th? You know this better than I do. I think it's the 13th of May when you have, no, the 9th of May, or is it the 10th? I think it's the 10th of May for the biology paper one. Whatever it is, you should know this, okay, better than I do. But I know that, yeah, it's about 4 weeks until GCSE, which is plenty of time. The 10th, thank you, O'Shea, the 10th is biology. Everybody's got biology, then it goes on to a bit of chemistry, then it's the physics. And I think some people start on the 9th, which I think is PB or religious education, I think. Okay, right, the next question is about energy, but it's also about the fact that we have a diagram. And I think this is a difficult thing about questions, is that they basically are a 2D representation of 3D objects that change over time. So we've got two balls of plasticine. They've got an equal mass. They're travelling in opposite directions and they collide with each other head on. So that one's going 8 meters per second to the right. That's going 8 meters per second to the left. Okay, as soon as they collide, they stick together and the combined object is stationary. During this time, the balls of plasticine do not interact with any other objects. So we have this kind of closed system. Now, the first question is something that I've covered before in this live stream. This is just a definition. I think people like Milkshake Zeno talking some good answers there. It's the sum of the kinetic energy and potential energies of all of the particles in the system. So this is a 2-mark question. Okay, let me get the exact definition. Oh. So a lot of you have already seen this. This is my AQA GCSE revision guide, completely free to download. It's a digital only download. In the back of it, I do have the definitions and internal energy. So this is, as far as I can see, the best definition I found straight from AQA. Internal energy is the total kinetic and potential energy of all the particles that make up a system. Okay, so there we go. So you're talking about the kinetic and potential energies of all the particles that make up a system. And so what we're talking about is not just like the big thing, but it's every atom or molecule inside this ball of plasticine. It's going to be vibrating. There's going to be interactions between that particle and one next to it. The slow-mo, free to download. Yeah, of course it is. Do you know what I'll do is, if you bear with me, I will put a link in the chat now that basically goes to that free download. So basically, if you want to download it, it's completely for free. I think it's about 100 pages in total. There we go. So if you click on that link now, it'll take you to physicsonline.com, my kind of main website, and basically put your email address. I'll show you what's in it, by the way. So it's got some stuff just about the exams. It's a bit about the course structure. That's just boring stuff. You should know that. There's a bit about how to revise. There's a list of all of my GCSE videos that you can find on my GCSE website. Then there's the content. It's got the different topics which I colour code. And then what you need to do is go through this checklist and just check things off as you revise it. Okay, so this is for all of the things. It's got even more information than the actual specification because I've got some diagrams, some of the shapes of graphs that you need. Suitable for anybody doing trilogy and also for those doing triple science. That's the stuff which has got like a blue bit of highlighting next to it. And then towards the end, again, there's like the space physics. I've got all of the required practicals that you need to know about, the maths that you need to know about for GCSE physics, a bit about your calculator. Here are the quantities in units. So the symbol, the unit and all that stuff. So you know that density is in kilograms per cubic metre, speed V meters per second. Equations, they're given to you anyway, so you don't need to remember them. Common circuit symbols that you should just know. I've got all the definitions for AQA, including the ones which are higher only, which are in bold, or triple science only, which are in blue. And then there's a bit about exam preparation, of course. There's how to use past papers, old spec papers, other exam boards. There's past paper tracker in the back, and then I've got a grade converter. So if you are doing AQA papers from before 2017, when you get your mark, they give you a grade which is A star to U, or to D really. Basically, what you need to do is you can use this to convert that A star to G grade into a 9 to 1 grade. And yeah, there's all of that stuff going back in time. So I've got the grade boundaries going back to like 2012. Yeah, now I don't have a hard copy of it for sale. It is only a digital version. So you can just basically click on this link that I'm just going to put up in the chat. I'll put a link to it as well beneath on my, where you can find it on my GCSE website as well. Where did I buy the calculator? I just bought this one about a year ago before they stopped selling it, and it's brilliant. But I'm afraid I don't know where to buy them. Okay, so what do we mean by internal energy? So I was getting a bit sidetracked there. So internal energy, as I've said before, it's a definition that you need to know. Get it on a flashcard. It's basically the sum of all the kinetic and potential energies of all the particles in a system. There we go, 2 marks. Right, that one there, you just need to know that. The next question says, compare how much energy is stored in different energy stores in a system before and after the collision, assuming no energy is transferred to the surroundings. So let's think about what's going on. So before the collision, we've got an object which has a certain mass and it's moving at a certain velocity v. And so the energy that that's got is in the kinetic store. So EK or KE is equal to a half mv squared. And there's also going to be the kinetic energy store of this as well, which is going to be equal to half times its mass times its velocity squared. So we can say that before, all the energy is in the kinetic store, because what we have there is something which is moving. Okay, right. After the collision, what happens? Well, afterwards, nothing is moving because V is equal to 0, and therefore the kinetic energy store is equal to 0. Now, the other thing is that these two things, they haven't gained any height, so the change in gravitational potential energy is going to be 0. So where's that energy gone to? Well, some of the energy has gone into the internal energy store, or we could say that the thermal energy store of the plasticine has increased. And that's because what we have is we've had a force acting over a distance, so there's this mechanical work, and the thermal energy store of the plasticine has increased as its temperature goes up. And of course, as time goes on, okay, I've got some good questions coming up, and I will answer your questions, everybody, including James, Milkshake, and other people like that, and also Premga Hill. So yeah, basically, we're going to compare the. So before, all the energy is in the kinetic store, the thermal energy store, the plasticine is increased as the temperature goes up, as the kinetic energy is now 0. Okay, so all of that kinetic energy has all been transferred to thermal energy or internal energy. Same thing. James says, are these questions harder than the actual ones we'll get in the exam? Yes, they are. Okay, I've designed these questions to be harder because if you do hard questions, then it really tests you. It really kind of probes to find where you don't understand things. And when you go back to doing lots of other past papers, they will seem easy in comparison. So it's very much that kind of train hard, fight easy. Okay. Right. Does anyone know a good predicted GCSE paper site? Yeah, just buy mine, okay? GCSE predicted papers, they're not really predicted. Nobody can predict what's going to come up. The students who are going to do well this year are going to get the top grades are the people who revise everything thoroughly rather than just trying to focus on what they think might come up based on what's happened in previous years. Can you view these questions for free on my website? No, you can't. They are all on the actual papers, I'm afraid. So they don't cost that much to get. Somebody says, how much is it? So basically each paper is $3.99, but that comes with the paper, the mark scheme, a set of work solutions, and if you then go to my website, which is GCSE Physics Online, you can then find a video, and if you've got a premium plan, that video then has like all of my video work solutions. So let me just show you that. So you go to practice papers on my website. There's information about them. You can also download a sample copy down here if you want to see what it's actually like. But you can basically, I've got the video explanations here. So for example, when you've got paper 1 alpha, all you need to do is you need to go to my website. You can then, maybe if there's a question you're not sure about, you just click on that and there'll be a video where I explain that answer in addition to all the kind of work solutions. Starts with a graph for a thumb. So there we go. I think it's worth it. Okay, James says that James, thank you so much for buying a set. James says, I've been using them and when I do AQA pass papers now, I find the questions easier, thanks. That's the idea, yeah. It's like you do these questions, they're hard, you kind of persevere, but if you do these questions, the idea is to really help people who want to get those top grades. People like you watching this tonight, the motivated people, you know, if you're wanting to get the kind of grade 7 and above, you need to be doing hard questions and that will make the actual exam questions a lot easier. Okay, so we now have this question. This one's difficult. The mass of each plasticine ball is 400 grams. The speed of each ball before the collision is 8 meters per second, and we've got the specific heat capacity of plasticine. Now, we know the temperature before the collision. Calculate the increase in temperature of the plasticine after the collision, assuming that the final temperature of the plasticine is the same everywhere. So, in order to do something with specific heat capacity, we know that the change in energy is equal to mc delta theta. Okay, and we're trying to find delta theta. Now we know the mass because we've been given it up here, so that's the mass. We know the specific heat capacity over here, but we don't know the change in energy, but we can work that out. So basically, we're going to look at the change in energy, and this is equal to the kinetic energy of this one over here plus the kinetic energy of the other one. So that's going to be equal to 1/2 times the mass v squared of this one plus 1/2 times the mass times v squared of the other one, which is just equal to mv squared. So the change in energy is equal to the mass, which is going to be 400 grams, so 0.400. Going to multiply it by the speed, which is 8.0 squared. Okay, so I'm just going to work that out. You always have to convert grams to kilograms. Milkshake, excellent question. Yeah, always convert from grams into kilograms. So we've got 0.4 times 8 squared, which is 64, which equals 25.6 joules. Okay, so that's the energy. Now, there's two ways we could do this. Okay, somebody says, go global, Layla. Is it okay to use the equation just because you remember that it is where it's used without understanding the full process going on behind the equation as you solve this problem? I reckon for GCSE, if you can just write down the equation, put some numbers in and you get the right answer, that's all that matters. They don't know necessarily the full process behind it, but I guess for this video I just want to really sort of explain my thinking and like the actual proper science behind all of it. Okay, so we know the energy. Now there's two ways we could do it. The first way is we could substitute the numbers in. So the change in energy is equal to 25.6. That's equal to the total mass that warms up. Now because we've got 400 grams in each ball and there are 2 of these balls of plasticine, that means the total mass is 0.800 kilograms. We're going to multiply that by the specific heat capacity, which is 950. And that's multiplied by the change in temperature. So we could say then that 0.8 times 950 is 760. So we could say that 25.6 divided by 760 is equal to our change in temperature. So 25.6 divided by that is equal to 0.034. And we want to calculate the increase in temperature. So to be honest, the temperature of each ball beforehand is irrelevant. Okay, we don't need to know that information for the question. And I think that's why physics can often be a little bit more tricky than maths, where in maths they just give you some numbers. Here you've actually got to work out which numbers are needed and which aren't. So this is 0.034 degrees. So I'm just going to write it down here, 0.034. And there we go. That question is, would that all be worth 6 marks in the real exam? I reckon they would never give you a question this difficult like this in a real GCSE exam, because I reckon about 10% of students would get the correct answer. Obviously not you lot, 100% of people watching this, you're awesome. But I reckon what they would say is calculate the kinetic energy of the ball of plasticine before the collision, calculate the total change in energy as the balls kind of slow down. Then there'd be another question where it says all of the energy is transferred to the thermal energy of the plasticine, calculate the increase in temperature of it. So what I would say is that for a GCSE exam, they'd break it down to like a 2-marker, a 2-marker and a 2-marker, rather than this multi-step 6-mark question. But if you can do this, then you're on for like a grade 9 at the moment. Okay, so yeah, hope that's all made sense. Right, yeah, I think I've kind of answered most of the things. A lot of people have actually helped out as well. So basically, yeah, people talking about the units, always use the standard units in physics. This is for A-level people who are joining the chat at the moment. So we're going to talk about energy in joules, mass in kilograms, length in meters, time in seconds. All of these things you need to make sure you convert from like the prefix to the actual unit. Okay, right, so that is the end. That is the end of the GCSE part of the stream. Hopefully everybody is doing all right. We're now going to go on to the second part. So this is the A-level bit. So if you're thinking about A-level next year, you're obviously more than welcome to sort of hang around with the A-level crowd. If you are A-level and you're joining for the stream, it's now after 8 o'clock. So hello everybody. Again, I said before, but I've been at this Ogden event. No, not Ogden. It's a British Physics Olympiad event today in London, where it was great to meet so many people. That's teachers, other people involved with the Olympiad, and people doing the international Olympiads and the astronomy one as well. So it's great to see so many people. Right, so yeah. So let's have a look at these questions. Now, again, for those of you who've just joined, if this is your first time to stream, hello, welcome. Make sure that you do subscribe on YouTube to stay updated. And basically, if you want to find out what we're doing for the next few weeks, just head over to alevelphysicsonline.com. I'm sure you've been there before. Click on the red thing that says live. It takes you to this page. And I've now updated next week's plan. So if you want to see what we're doing next week, you can click on the date. Say, for example, on the 1st of May, which is Thursday maybe. You can then find that, oh, here we go, that on the 1st of May, we're going to be doing a Planck constant practical. And we're going to do another Planck constant practical, this time using like a photocell thing. That's going to be next week. So this is some of year 12 stuff being revised for those of you in year 13. But there's loads of stuff here. And if you want to download stuff, just click on download and you can download the questions so you can do them beforehand. Look at this beautiful bit of simple harmonic motion going horizontally. So tonight we're going to be looking at G on a slope and with an interrupt card. So this is just 2 more ways that you can measure the acceleration due to gravity. And last time when we had the stream a couple of days ago, I think we did G by the trapdoor method, but these are a couple of alternative ways of measuring the acceleration due to gravity. Okay, right. Ben says, I might have missed out a bit of the EduCast materials because you can't find anything on polymorphous or crystal things. I think you're right. I don't think I included a video of that when I did those videos originally. And it's quite an interesting topic, to be honest, like having done engineering at university and like looking at material science. It's a really interesting area, but I'm afraid I think I might have missed it off, Ben. So apologies. I would say that my videos cover like 95% of the actual specifications. So I think I cover pretty much all of the basics. But Ben, I think I might have missed that one out for EduCast. Okay, should we just get going with some other questions? Right, so a large marble is placed on a smooth slope as shown below. The slope is at an angle of theta to the horizontal. So I'm just going to start labelling this. So we know that angle in there is theta. Add labels to show the weight and the components of the weight parallel and perpendicular to the slope, W sine theta and W cos theta respectively. So all of you know this. This is like your standard object on a slope. In terms of where you put the force arrows, there's no definite way that you have to do it. Some people add them where the objects touch. Some people put the weight acting from the centre of that object. I'm going to go from the centre of this. And I'm just going to draw an arrow down here, which is W. Okay, now there's going to be, I'm just going to use my ruler here, and actually I suppose if I use my protractor, and I kind of make sure the protractor is pretty much parallel with the slope, 90 degrees to that kind of comes to about here, and what I'm just going to do here is put in a construction line. Okay, so I've got one line that kind of does that, that's parallel to the slope, and there's going to be another, perpendicular to the slope, and there's another line parallel. Okay, now the first thing is which of these angles here is theta. If you've done lots of questions on this, then you should realise that we've got like that triangle there is kind of similar to this one. So if that's theta over there, then this angle here is going to be theta. So I'm just going to label that, okay? It's my diagram, I can label it how I want, and that's the best way to do it. Now, what we then have is effectively the other sides of a right angle triangle. So we basically have something in there a bit like that. Okay, now the length of this side here, which I probably should have drawn with the ruler, is going to be the component of weight perpendicular to the slope. And we also have, if I just put in again like a kind of sort of construction line from the end, which is going to be parallel to that perpendicular line. We also have, I should draw this with a ruler, we have this force down here. Okay. Right. Vegetaval, does minimum GPE always equal max kinetic energy for simple harmonic motion? It depends on the system, but generally yes for a pendulum, no for an oscillating vertical spring, because when the spring has minimum gravitational potential energy, it also has minimum or zero kinetic energy because it's going to be at the bottom. So only for a pendulum, yeah. Okay, going off topic a bit. Okay, so what we have here is we have something where we have effectively the hypotenuse, the adjacent, and so this one over here is going to be sine and this is going to be cos. So this one here is going to be equal to W cos theta, and this one up here is going to be equal to W sine theta. Now I'm hoping, if you're in year 13, you can just almost immediately identify which is cos and which is sine. The thing that I think is quite useful is like this here is like the closed angle. I can't remember who said that, but it's basically the closed angle because the angle is closed by these two things, and therefore it's cos. Okay, that's like a very simple way to remember it. Why does it say 15th of April? Oh yeah, that's a good question. It says the 15th of April because this question comes from my daily workout book where I've got questions, and basically I've got questions for every day of your A-level course. And in the first year, because this is book 3, so it's the third book in the first year, on the 15th of April you could do these questions, on the 16th you do those, on the 17th, 18th, 19th, and basically if you do this it will keep you structured and basically get you to do a little bit of physics every day. So this book here has questions for all of April, all of May, all of June, and this is basically going up towards the end of year 12. And then the idea is that you get, if you want to, book 4, and then book 4 goes from questions through July, August, September. You can see now the content goes to more like year 13 style stuff. September, SHM questions, going through to October, stuff to do with like magnets and gas laws and kind of more kind of interesting physics. So that one there is book 4. Okay, that's why it says on the top 15th of April. Right, calculate the mean time and use one of the CVAT equations to calculate the acceleration in the table below. So we've got some data here. The first thing I think it's always worth doing is looking at the data, checking for any anomalies and getting that. There's no anomalies here, so all that data looks good. The first thing to do is just calculate the mean, so we're just going to add the numbers up. So 0.32 plus 0.28 plus 0.31 divided by 3 is 0.30. And then this one over here, 0.28 plus 0.28 plus 0.26 divided by 3 is equal to 0.27. Okay, so that's the first thing. The next thing is we need to work out the acceleration. Now, if you're not sure, for something like this, it's worth just writing down, because it's a CVAT question, so let's write it down, S, U, V, A and T. Okay, do we know the distance that it's gone? Yes, we do, because it's rolled 30 centimetres down the slope, so that's 0.30 metres. Now, it's going from rest, and therefore U is equal to 0 metres per second. We don't know the acceleration, but we do know the time because we've worked out the mean time over here. So we need to think about which equation doesn't have a v term in it, and therefore we can say that S is equal to ut plus a half at squared. I'm sure if you are doing A-level physics, you're going to be super familiar with all of your CVAT equations, because you've done it in maths as well, a lot of you, and you've done it maybe at GCSE in maths. So basically T, or U is 0, so that's that. So S is equal to a half at squared. So T is going to be equal to 2S over A square rooted. Okay, does that make sense to everybody? This is the way. Oh no, sorry, we're trying to find the acceleration, aren't we? So the acceleration is equal to 2S divided by T squared. Okay, yep. So this is the equation that we need to know. So we need to just do 2 times 0.30 and divide that by the mean time squared. Okay, does that make sense, everybody? Hopefully that's all right. So using that equation, we've got the value there, so 0.36 squared, and then we're going to do 0.6 divided by that. The acceleration here is 4.6. Okay, so we're going to leave it to 2 significant figures. We then have 0.3 squared, and 0.6 divided by that is 6.7. And then we've got 0.6 divided by 0.27 squared, which is 8.2. There we go, that's all it is. So this is just following on by like putting that information there. So calculate the mean time, so we've done that, and use one of the CVAT equations to calculate the acceleration, which we've done there. The last thing we're going to do is calculate values of g sine theta, where g equals 9.81. So we've got angles here. So all we need to do then for this one over here, we've got 9.81, which is our value of g. We're going to multiply that by sine of 15, and I'm just checking here that the calculator is in degrees, and that gives me an answer for the first one of 2.5. This one over here, we now have sine 30, so I'm just going to delete those two, type in 30, and that's equal to 4.9. Delete those and put 45, So that's 6.9, and then it's going to be sine 60, which is going to be 8.5. Okay, so all we've done here is we've... Oh, here we go. Some good questions there. Everybody loves this question. How do I show the previous answer? It's just, I think actually shift setup. So shift setup. Number 1 is the input output. And I think number 3 is line input, line output. As Moodle Mip said, thank you so much. The names are difficult to see. Yeah, so people have got that. Right, so we've actually worked out the acceleration of the ball, and we've also worked out g sine theta based on the angle of the slope. And we're going to compare the values in the last 2 columns. So what we can see here is that the acceleration of that ball is just very slightly smaller than g sine theta. Now, this is the actual acceleration that's actually been measured in that experiment, okay? Because what we've done is we've put the ball on a slope and we've varied the angle and we've just worked out the time it takes to go from here down to a certain position. And we can see that the actual time, as the slope gets steeper, the time gets smaller. But this is a nice way to measure, quite a long time compared to if we just dropped the ball vertically. We then worked out g sine theta, which is the acceleration of that ball based on the fact that there's going to be the component of weight acting down the slope is going to cause this acceleration, and that's the expected theoretical acceleration of it. And what we find is that the real acceleration is slightly smaller than that. So, right, why do you reckon that is? Why do you reckon the actual acceleration of the ball down the slope is less than the theoretical prediction? So people in the chat, I know there's a lot of you probably just lurking around there. It's time to subscribe on YouTube if you haven't already done so. Maybe like the video, and also you can press the heart button. I think that just does some nice stuff on YouTube. And if you could let me know, air resistance, slope isn't actually smooth, friction, riptides kill, friction, not accounting for drag, just a person, friction. Did it say the slope was smooth? It does say smooth slope as shown. So I guess there will be some friction in real life. I think the word, strictly speaking, I think you've caught me out here. So the word smooth basically means that there's no friction. But I would say in real life, even if it looks smooth, there's going to be some friction. And I think that we've got, resistive forces. There might be air resistance. There's going to be friction between the slope. So that's one thing. Another reason could be there could be an error, so maybe systematic error in the timing. It doesn't say actually how the time was calculated. So potentially there could be some error between letting the ball go and actually pressing the stopwatch. They assume that the acceleration is constant. Yeah, it might be that there's initially this acceleration, but then as it gets faster and faster, the drag forces are going to increase. So as it's going quicker, the air resistance, which is often proportional to like v squared or v cubed, that might increase. So timing errors could be another one. So there might be all sorts of reasons. So this is another method that rather than dropping something vertically, because the problem is when you drop something vertically, if you drop it by a meter, it takes a very, very short amount of time for it to fall to the ground. If instead you put something a meter up a slope and you let it go, it's going to take much longer to drop, and therefore it's going to reduce the percentage error or percentage uncertainty in your timing results. So there's loads of different reasons, and it's great to see everybody here thinking about that. So that is another way that we can measure G. Has anybody with a handy teacher who's got some handy technicians and some handy light gates, has anybody used an interrupt card like this to measure the acceleration due to gravity? So again, this is about lots of bits of physics. Some of it is just speed equals distance over time. But there's lots of things. Somebody says, do you then calculate the constant in the equation for friction? I guess you could in the previous one. You could probably work out the coefficient of friction. Somebody used a trapdoor. Yeah, that's what we did last time, which is definitely a correct method. But like anything, there's often more than one way to measure it. So a lot of people have actually done this. Some people haven't. Somebody auto-calculates the speed when it hits the bottom. Now, of course, in the exam, I don't think they're going to give you a nice, easy question about a practical that everybody's done. So they might introduce something like this. And a lot of this is common sense. It's a motion problem, but it's a motion problem where you might use SUVAT, but it leads on to a calculation of a physical constant like the acceleration due to gravity. So I'll just let you read the question. And I think anything like this, you should always add stuff to the diagram. Okay, so we've got a light gate and a double interrupt card to find the acceleration. The light beam is kind of like basically here. The card is a square card, and it's got a square hole in the middle, and that's 15 centimeters. Right, so this is going to be 15 centimeters from here to here, and it's got a 5 centimeter hole in the middle, which means that this bit here must be 5 centimeters, and this bit here must be 5 centimeters as well. So the first thing I've done is taken this stuff here, I've added it onto my diagram, and just kind of started getting these dimensions. Okay, we've got a time of 100 milliseconds as it first interrupts. So it's, as this 5 centimeters passes through the light gates, it takes 100 milliseconds. And then it takes 34 milliseconds as that second bit of card falls through. Now, I probably should have made one, but I didn't actually have time today. Okay, what's the initial velocity of the bottom strip of card from P to Q as it interrupts the beam? So we know that, I'm going to say U, the initial velocity, is equal to the displacement divided by the time. So the average speed, or the average initial velocity, as the bottom part of the card goes through the light gate, is going to be the distance, which is 0.050 meters, because it's 5 centimeters. And we're going to divide that by 100 times 10 to the minus 3. Okay, now of course you can just do that in your head because it's 0.05 by 0.1. But again, if you're in a real exam, you can make mistakes trying to do stuff in your head. So I'm just going to divide it by my calculator, which is equal to 0.50 meters per second. Okay, what's the final velocity of the top part of the card as it goes through? Well, the final velocity is going to equally be the same displacement here, divided by the time taken, which is still 5 centimeters, but now it takes less time because it's travelling faster because it's accelerated due to gravity. And the time is now 34 milliseconds, so 34 times 10 to the minus 3, which is equal to 1.47, which I guess is, I'm just going to write it down as 1.47, which equals 1.5 meters per second. Okay, so it goes from 0.5 to 1.5. Okay, now we need to calculate the acceleration of the card. So, what should be the first step that I should write down in my working out to calculate the acceleration? What would be the first thing you do if you've got objects which are accelerating? So let me know in the chat what you would be doing first. Okay, Joe Smith, McRae God, Hernandez, yeah, all of you, gold stars, big shiny stickers, SUVAT, light, Arjun, yeah, so I'm just going to write down SUVAT. And it doesn't matter how good you are at physics, just write this down first of all, and that just allows you to identify what you know, which saves you time because you'll get the right equation first of all. So the distance between them, what's the distance that's going to be between these two bits of card? So that's, I think, one of the trickiest bits. We know that we've calculated the initial velocity of 0.50 meters per second. The final velocity is 1.47 meters per second, so I haven't rounded down just yet. The acceleration is due to gravity. It's the first S over T because it's horizontal, yeah. So basically, it's going to be falling down this way, and so the amount of card that goes through the light gate is equal to this distance here. So basically the whole thing falls down like this. Okay, so what is the distance between these bits of card? Is it 5 centimetres? Is it 10 or is it 15? I reckon my answer would be that basically if we start here for the first one and we start timing here for the second, I would say that the distance that it falls through is equal to this, which is going to be equal to 10 centimetres. So the displacement is 0.10 metre. Okay, so we've got some CVAT stuff. We don't need to work out that. We don't need to know that. We can say that v squared equals u squared plus 2as. Okay, and that means the acceleration of a is just equal to g. So we can say that v squared minus u squared over 2s is equal to g. Okay, and that's just equal to this number here. So I'm going to do it in blue. 1.47 squared minus 0.50 squared divided by 2 times 0.10. And when you do that, this is equal to 9.6 meters per second squared. Okay, so that is the answer. Of course, it's always worth just thinking, is that sensible? And it's about 9.81. It's similar to 10. It's maybe a little bit slower because maybe there's some air resistance. How many marks would I reckon that would be? I reckon that's 1 mark, that's 1 mark, and that's 3 marks. Would be my rough approach, I reckon, because that's just distance over time. That one there's the same as that. I reckon they'd probably have a show question, so show that the initial velocity was 0.05 meters per second. Show, and then, or they might give one of these. They might say, they might, yeah, I don't know exactly, but I reckon it'd be worth like 4 or 5 marks in total. I didn't really type that quick. I actually have, just to confirm I'm actually doing the right thing, I do have my work solutions here. And by the way, when you buy book 3, in addition to the fact that in the back of the book there are all of the answers, on my website at A-Level Physics Online, you can also download a full set of written work solutions to everything to kind of see like the approach that an expert would take. You couldn't use time because we don't know the time. We know the time that it's interrupting the light gate for, and we know the time that it interrupts the light gate for the second time, but we don't know the time between these 2 measurements being taken. And that's why we didn't have a value for time in that question. Okay, the last part is suggest a couple of advantages of attaching small masses along the bottom edge of the double interrupt card before it's dropped. So why, imagine we had some blue tack, or you had some bits of lead weight that you could attach to this. If you attached these bits of blue tack over here and then drop the card, what would be the advantage in that? So what do you reckon the advantage is? So it doesn't fall flat down. I can't remember what I actually put when I wrote this, so I'm just going to check. Yeah, so basically it allows it to fall vertically. If it's falling vertically, then there's going to be effectively, you know, the side that's going through the air is going to be quite small, and it stops it sort of going to the side like this. The other option is if it didn't fall vertically. So imagine we had like a side view. So here's my light gate, okay, and here's the beam, this kind of invisible infrared beam. We want the card, so this is the piece of card here, we want it to fall vertically through so that exactly 5 centimeters cuts that. Now, if instead that started to fall at a bit of an angle and this whole thing fell through and went through the light gate, it might be then that rather than 5 centimeters of the card actually cutting it, we might have maybe 3 centimeters of card actually cutting the light. And that means, although we might have an accurate measurement for time, we'd have a smaller distance, and therefore we'd have a higher, a smaller distance, and therefore we'd have a lower velocity of card. Okay, so it keeps the card taut, and yeah, it basically means that we actually get 5 centimeters falling and actually cutting that light gate. And I think as well, you can buy, I think Philip Harris do one of these things where you have like it's like a transparent piece of plastic, and it's got black lines on it at regular intervals. And you drop this whole thing through, you get like 8 or so readings, and you can then see how the time between readings gets smaller as it accelerates. So this question here was, again, just another way that the acceleration due to gravity can be measured. And this is called a double interrupt card because we've got 2 bits of card. So we've got something which is doubled, and they basically interrupt the light gate 2 times. But again, you could probably have it with many ones. There might be different variations of this. Okay. For questions A and B, aren't we assuming that for 100 milliseconds a card is travelling at a constant speed? I would say that what we've done here is we've calculated the average velocity, and here we've got the average velocity. And effectively what we're looking at is the average velocity here, the average velocity here, and then the time between those. Yeah. So it will be accelerating. And I guess this is just maybe one of the limitations. So we don't know the exact instantaneous velocity, but we know the average velocity at that time. Okay, I reckon that's it there. I'm going to have time off tomorrow because I'm not going to be doing stuff on a Friday night, as neither you lot should be either. So, treat yourself, have a rest tomorrow night, have a rest Saturday night at 8 o'clock. But I will be back here, hopefully. I'm going to be in Manchester on Saturday and Sunday, so I'm hopefully there shouldn't be too much traffic on the road, so I will be back in time for the Sunday night live stream. I'm going to be live from 7:30 doing GCSE, and then I'll be doing A-level stuff at 8 o'clock. I will try and do more past paper things. I think next week in my plan I do have kind of some past paper style questions on the Wednesday, I think, or the Tuesday. But what I've got to be really careful about, and this is the only reason I'm not doing more AQA past paper stuff, is because of copyright issues. And basically AQA, it's not actually the science team. The science team at AQA are brilliant. They're like really supportive. They know what I'm doing. They like it. But it's like other people in AQA who don't like any AQA materials going onto YouTube. So that's why, due to copyright reasons, I can't show the real AQA papers. However, if you want to find lots of AQA questions that I have done, head over to Physics and Maths Tutor. Actually, let me show this to you. All of you should know about this. And this is for everybody doing any A-level. Let's just find this. So if you go to Physics and Maths Tutor, I know, play music today. This is a different Physics and Maths Tutor. Right, so that's... So... basically, if you go not to PMT the guitar people, I know this is another bit. Okay, if you go to Physics and Maths Tutor, all of you know the website, you've all been there. Now, if you go to Revision and you go to Physics and you look for A-levels from 2015 and click on AQA, I'm sure if you're doing AQA, you've already seen this. Now, there's lots of topics over here. Which topic do you want me to choose? So we've got paper 1, A-level paper 1, A-level paper 2. Which one do you want me to do? Paper 1 or paper 2? I reckon people are going to choose paper 1 because it's coming up first. Turning points. Okay, apart from turning points, which one should I do? Paper 1. Okay, so which part of paper 1? Do you want me to do waves, mechanics, electricity, further mechanics? Which bit of paper 1 do you want me to choose? If I just zoom in a bit more. It's a little bit blurry, unfortunately. And what I'll do is I'll show you what I've got here that I did for Physics and Maths Tutor. Electricity, that's the first one I've seen. Yeah, 2 people electricity, just a person, IDK. Loads of people, do people not like electricity? Okay, so if you click on electricity, what you see here under multiple choice, it says MA. So anywhere it says MA, these are the model answers. People don't like electricity. So current electricity multiple choice questions. For all of these questions on here, you'll see, and you might recognise this handwriting. So what I've got here are my work solutions that I did with Joe, who works with me. He did most of the work, to be honest. But yeah, basically, we've got all of these work solutions to all of the multiple choice questions. So as you're revising, this could be helpful. And it's the same for any of the topics on Physics and Maths Tutor. So you look at Chapter 8, Nuclear Physics, questions by topic. You look at the this one over here. You can see, again, all of the questions to do with radiation. You can see it's sort of done by me because it does say A-Level Physics Online on it. You can see all of the work solutions for all of the multiple choice questions for that. Now, somebody said turning points. So if we look at turning points in physics, they do have questions by topic, but they don't have my model answers. So what I do have is on my website, I have done some of these, but I think they haven't been updated yet. So if you want to find all of the work solutions, you can find them at A-Level Physics Online /PMT Solutions. And basically down here, you can find the turning point ones. So if you want to find the work solutions to turning points, until Physics and Maths Tutor put them on their website, you can see my own work solutions to these questions done by topic. So there's a lot of stuff out there. So that might be worth having a look at. Yeah, right. So plenty of stuff. Jacob, you love the solutions. They help so much. Thank you so much. I'm really pleased they're useful. James as well. And actually, I met some students today from a school in Bristol when I was in London, and they did like a really good practical project for the Physics Olympiad, and I think they've been using them as well. So yeah, hopefully that's all good. Hopefully all of you have a lovely bit of a restful weekend after school tomorrow, and I'll see all of you on Sunday. And don't forget, if you want to buy stuff, you can do that in my Physics Online shop or on my website. But thanks so much, everybody. I'll see all of you soon. Thank you.